Our last unit in astrodynamics is a brief survey of a lot of the different spacecraft subsystems. So we'll call this astrodynamics number 6, Spacecraft Subsystems. We're just scratching the surface on these systems because as communications engineers, we need to be aware of their limitations, what they're trying to do, how they affect other systems and subsystems on the spacecraft. We're not necessarily going to design them ourselves, but you need to know that they exist. And who knows, maybe you might be designing them. Because a lot of these subsystems require quite sophisticated electrical control theory and programming and design. So they're very important parts of the spacecraft, even though we are going to be concentrating on the RF and the communications part. We need to know how they fit into the general pieces, how those pieces fit into the puzzle of a final spacecraft design. And so one of the first systems that we need to be aware of are the launch systems. There's no way that we know of to get a reliable spacecraft into outer space at a reasonable price without rockets. We use rockets to launch satellites. And rockets are usually launched with the rotation of the Earth. I think I mentioned this in an early lecture, but just in case I didn't. Most satellites launched with the rotation of the Earth by the rocket. And the reason is, this is the launch system is really almost always for most missions anyway, the most expensive part of the mission. Well, I shouldn't say that because there's some really expensive satellites up there. But this is a huge part of the cost, let's say. Just getting the mass into space. And we understand why, right? We've calculated in this class that in order to get something into low Earth orbit, you got to be moving at least 7 kilometers per second when it gets up into space. And we're starting off with just a few hundred meters per second with the rotation of the Earth. So we have to add a lot of kinetic energy, and we have to overcome 1,000 kilometers of potential energy, gravitational potential, as well on top of that. And so every little bit helps. And so the fact that you launch with this rotation of the Earth instead of against it means that you don't have to overcome that initial few hundred meters per second that the rotation of the Earth imparts to you. That's a substantial rocket fuel savings, actually, and it reduces the cost. So much so there was even a company, I don't know if they're still in business, but they were called Sea Launch. And this company took an old oil rig and outfitted it to be a launch pad for a rocket. And for a private company, for a fee, they would float up to your country, grab your rocket, float down to the equator, and launch for you at reduced cost. And this was a good deal for a lot of things like Scandinavian countries and people that don't have access to a tropical launch site like Florida or Texas or Southern California. So if it is not launched with the rotation of the Earth, and there are lots of applications where you don't necessarily want that, that is called retrograde. The orbit is retrograde if against the rotation of the Earth. And we often denote that by saying that the inclination is greater than 90 degrees. That is, I'm going around the Earth. This is 0 degrees of inclination as the Earth rotates along with it. If I tilt this above, beyond the pole so that I'm greater than 90 degrees inclined, now my if I'm looking down at it, my orbit has effectively reversed polarity with respect to the rotation of the Earth. So that's another way to denote a retrograde orbit with a negative inclination. Rockets are the only way that we know to escape Earth's gravity, and they require a tremendous amount of fuel. Now, I'm going to give you the working definition. Well, before I do that, let me chart what is the typical path that a rocket takes to get into low Earth orbit. So you start off with your stage 1, and this is basically at t equals to 0. You have ignition and liftoff. So let's draw a rocket on the launch pad. Here's the Earth. Could be some scaffolding here. So you launch your rocket. The stage 1 burns out. That's your first bottom stage that has a lot of the fuel that you use to initially get off the ground. That burns for about 160 seconds is a typical number for that. And then after that, shortly thereafter, you get separation. So the second stage starts to go active. And the bottom part, the first stage, kind of falls back to Earth. And at this point of burnout, you're somewhere between 75 and 85 kilometers, roughly. Somewhere in between there when this happens. Now, how high does a commercial airline fly for perspective? 30,000 feet. Can you convert that to kilometers in your head? 10,000. That's good. That's reasonable. So relative to this, your highest aircraft is about there from the ground. It's obviously not drawn to scale. But just to give a little perspective, this is very high up in the atmosphere. Really, you're on the edge of space already. And then, finally, when you get up to about 330 kilometers, you're beyond most of the atmosphere, and you can actually start a stable orbit here. You're in low Earth orbit, on the fringe of a useful low Earth orbit. Your velocity is over 7 kilometers per second, and the time from the launch is about 565 seconds. This is when stage 2 burnout and eventual separation occurs. So really, it doesn't take long to get into space, right? What is that, about 10 minutes? You have to get into space in 10 minutes. Otherwise, you don't have the kinetic energy to stay in space. So most launches are very similar to this pattern in the way that they unfold. Now, after this, you can do all sorts of other things. You know, maybe you're going into higher low Earth orbit. You're going to have another stage that kicks in and drags this thing out to medium or middle Earth orbit or high Earth orbit. But the first stages always looks very similar to this in terms of their time and altitude and construction. And at this point, there's payload deployment too. You may have multiple satellites on your spacecraft at this point after the stage 2 is burnt out. And this is where you start launching your payloads. Okay. Now, what is a rocket? I'm going to give you Well, first I would like to hear the aerospace engineers. If you had to define a rocket, what would you call it? How would you do that? Did they do that in orbital mechanics? Oh, nice. Pass the buck. Well done.
The thing that shoots mass out of that.
Okay, that thing that shoots mass out of a nozzle. Is that what the thing at the bottom is called, right? The nozzle. The nozzle. That could be the same definition for a water gun. But it's a good first attempt. Let me give you the electrical engineering definition of a rocket. We'll see if I get any closer. This is all you need to know. A rocket is a bomb with a hole in it. Chemically, it's very hard to tell the difference between the two. It just so happens that there's a hole in the rocket, and the mass gets shot out at very high velocity, and that's what actually gives you the thrust. But chemically speaking, what goes into making a bomb and what goes into making really good rocket fuel is almost the same. What is it that goes in there? There's a couple things that are always kind of characteristic of rocket fuel. We're going to give you a little chemistry lesson now because it's good to know what goes into making a rocket, and also what goes into making rocket fuel for station keeping, which requires a little finesse. So, for example, you always need a fuel. And all these fuels, I'll give you a couple examples of what fuels look like chemically, but they always have nitrogen in them. Nitrogen, just like an explosive. Good fuel is an explosive. So we have a fuel, which is a nitrogen-rich compound, typically. Nitrogen solid or liquid, because we want something that's going to be very compact, that gasifies when it reacts and expands so that you get that propulsion, that you can focus and steer. And then we also need an oxidizing agent to facilitate the reaction. And so, for example, let's see. I'll give you an example of oxidizing agent. We'll use a chemical formula. We're going to do some chemistry in this class. N2O4, nitrogen tetroxide. If I drew out the bonding of this thing, it's basically 2 nitrogens and 4 oxygens. How do these molecules, or how do these atoms organize themselves in a molecule? Well, you remember from your freshman chemistry, nitrogen has 3 hands that it likes to share with other atoms. So there's going to be one with itself, and there's going to be some oxygens. Oxygens, how many hands does oxygen have? 2, that's right. So they're basically going to shake hands on the end. And that's basically what the molecule looks like. So 2 triangles of nitrogen dioxide stuck together. And this is an oxidizing agent. It's an agent that wants to separate very easily and energetically. It also contains nitrogen. That's also convenient. And it supplies oxygen to the reaction very quickly. And so you've got nitrogen tetroxide. And then we need a fuel. And I'll give you 2 examples of fuel that we keep on board the spacecraft. They're very similar to each other. Monomethyl hydrazine is a very common rocket fuel. N2H3CH3. And if we draw this out, nitrogen, 3 hands. And I'm going to put H's over here. Monomethyl, which means there's a methyl group. CH3 is a methyl group. CH3 by itself is methane. CH4 is methane. You take the H off and you make it bond with something, and you get a methyl group. And a slight variant of this, which is also used in rocket fuel, is unsymmetrical. Dimethyl hydrazine. And of course, that just has a slightly different formula. And in this case, you've got 2 nitrogens, 3 hands each. One has hydrogens, the other one has methyls on it. And so, to illustrate the efficacy of rocket fuel, we are going to do a little bit of something that you may not have done since your freshman year of college. We're going to do a little bit of stoichiometry. Do you remember those problems? I already see by some of the pained grins that you do remember some of it. Others have put it out of your memory completely. This is the whole balancing chemical equations and reactions. This will be a blast from the past. What goes into rocket fuel? Okay, we're going to take, let's start with just monomethyl hydrazine. Let's just do an example with this. Plus our nitrogen tetroxide. And what are the things that are going to come out of this reaction when we put them together? Both of these are liquids. This is kind of a brownish liquid. This is a liquid fuel. Well, nitrogen gas. In fact, this is one of the reasons why this reaction is explosive. Nitrogen has 3 hands. And when it encounters another rogue nitrogen, it would love to share all 3 hands with the other 3 hands of the nitrogen. So nitrogen, well, it's N2 in its chemical formula, but it looks like this. And this is a very preferred low energy state for a gas. It's the reason why 80% of the air is nitrogen diatomic molecules. Nitrogen loves to be in this state. It's a low energy state. It releases all sorts of energy to get to that state. And it's a gas. Now, there's some other things in here that have got to turn into something along with the nitrogen. The 2 common ones, there's going to be some water, because we've got H2O. And there's going to be some carbon dioxide. Let me make sure I stay on the board here. CO2, because this is essentially a form of combustion. And I've accounted for at least all the different elements that show up on both sides of the equation. I have not balanced this thing yet though. So let me give this a shot. Let's say I'm going to give you 2 minutes. Who thinks that they can balance this equation? Just take a deep breath. I'll give you a minute. Just think it over. And tell me who can balance this. We'll see who remembers their freshman chemistry the best. See that a good many of you either have the answer already or have given up. before this even started. Okay, if anybody thinks they have the answer, just raise your hand and shout out the numbers that I should put in front of here, and I'll verify your ability. This is way cooler than Sudoku. I once asked this in a SATCOM class with over 30 people in it, and nobody could get the right answer. I asked the same question in a SATCOM course over in the Shenzhen campus with 5 students, and all 5 students got the right answer. Not to make you feel ashamed or anything. Does anyone think they have it? Oh, okay, good. The aerospace engineer. Come on down and introduce you. Do you mind being in front of the camera and writing the answer up on the board? Oh, yeah, sure. If you want to be anonymous, that's fine, too. You can just shout out the numbers if you want.
Sure. So, 4, 10, 32, and 4.
32 and 4. Okay. First of all, thank you for not simplifying this. You could have divided by 2. But that's okay. That's okay. And let's see. Does this all balance out? Well, I've got 10 times 2 nitrogens, 4 times 2. That's 18 nitrogens. And I only got 20 nitrogens on the other side, so slightly off. It's okay. Nobody ever gets it in this class on the first try. Did anybody else get it? These are tricky problems. You either have a knack for stoichiometry or you don't. There's no real formula for doing this stuff that I'm aware of. Okay, while you plug away in that, I just want to point out a couple things about this. I said that these 2 molecules are solids or liquids when they're kept in a vessel under a little bit of pressure. All these are essentially gases, especially when they're hot and they're done. That's really what you want in an explosive. You need an explosive for your rocket. You need something that's going to rapidly turn from a small volume object into a very hot, energetic gas. Remember the gas laws that you learned in chemistry. The volume that a gas takes up, what was that law, if you wanted to calculate that? Do you remember that formula? PV equals nRT. So it says the volume is going to be proportional to the temperature. So you want something that's going to be energetic and hot. And it's also proportional to the number of atoms. The actual shape of those atoms has very little to do with how much volume that it takes up. So you want a lot of hot, energetic, lightweight gases that kind of expand to a very high volume quickly. If you do that in a rocket nozzle, you shoot everything out in one direction. You impart a tremendous amount of momentum to your propellant, and since every reaction has to have an equal and opposite action, the rocket goes in the other direction with the opposite amount of momentum. So that's energetic, hot, energetic gases. Okay. Charles, do you have an answer for me?
I think so.
Oh, thank you. Let's try.
4, 5, 9, 12, 4.
9, 12, 4. 9, 12, 4. Correct. That's the correct answer. Well done. You are a seventh level chemistry master. Well done. Specifically, we were talking about launch systems. Launch and propulsion. So we talked about rockets, the basics of how a rocket works. You have lots of different types of rockets. You have chemical rockets. You have liquid fuel rockets. Even something as simple as hydrogen and oxygen can make a rocket fuel if you compress these into a liquid form that don't take up a lot of volume. When you combine them, you get hot gas coming out. And this is a nice rocket fuel to use anyway because for a couple reasons. First of all, if you've got H2 and O2 along for the ride, you have a source of electricity as well. If you have fuel cells, you can generate electricity with this reaction when it's much more small and confined while you're out in space. And, of course, we did some stoichiometry last class period, remember? It was a much more complicated expression last time. That was I believe it was, what did we do? Monomethylhydrazine and nitrogen tetroxide. Those two liquid fuels and how they make a bunch of hot gas particles that are very good for rocket propellant. Hydrazine is also often used in space as a station-keeping fuel. Because it's a liquid fuel, not unlike hydrogen and oxygen, and I can't stand it any longer. I need to balance this equation. Sorry. I wanted to interrupt this and make sure that that was balanced. This is also a liquid fuel. What's the nice thing about a liquid fuel compared to a solid chemical fuel for a rocket and propulsion? Aerospace guy.
You can throttle it.
You can throttle it or turn it off completely, right? That's right. You can turn it off. In fact, for the longest time, as a policy, NASA would only send manned missions into space using liquid rocket fuels like this. So if you look at if you go down to Cape Canaveral and you tour the Kennedy Space Center, you look at the Apollo rocket, the rocket that went to the moon. They actually have a real Apollo rocket laid out on its side, an incredibly impressive structure. And it's all liquid hydrogen and oxygen tanks and miles of plumbing, what looks like, to combine these in the different stages it took to send a group of people to the moon. And it would have been much more efficient weight-wise and size-wise to use a chemical rocket at that point. But once you light the firecracker, you're not turning it off in a chemical rocket. And so this ability to abort a manned mission. Only recently have chemical rockets become reliable enough where NASA now puts manned space missions on chemical rockets. The shuttle, of course, had both a combination of chemical solid rocket boosters on the side and liquid fuel in the main tank for that stage. And so the moral of the story is you take something that's very compact, a liquid or a solid fuel, and you make a hot gas as a propellant. And this is pretty much how you get into space. And it's also how you do basic station-keeping operations when you're in space. Now, however, once you're in space, you do have a few alternatives to solid rocket fuel. One of the ones that's being used more and more nowadays is the concept of an ion drive. And to understand this, I have to understand something that is kind of a dying art nowadays, the science behind ions and charged beams and things. When I first got to Georgia Tech in 2003, I was teaching undergraduate electromagnetics. And that fall, I had a nice-sized class of 50-plus students. And I prepared a whole lecture complete with really nice-looking animations and explaining how a cathode ray tube works, right? Because it's a beautiful electromagnetics problem for students that are learning electrostatics and magnetostatics. It's a wonderful illustration. that they used every day, right? So he said, well, how does the cathode ray tube work? You have this nice vacuum tube. Cathode is over here. This is the thing that's emitting the electrons. You have a screen, a mesh screen here. This is your anode. And a very high DC voltage applied between the two. So this is actually applied to a little plate of metal that has an annulus here. In an attempt to, you heat up the cathode, those electrons are getting ready to jump off because it's glowing hot. They jump off here, and of course, the electric field points, we've got to get the polarity right. Let's see. Electric field should point this way, positive to negative. Why? Because the fields, in this case, are going to point this way, and the electrons are going to want to go opposite the electric field because they're negatively charged. So they jump off through here. There's usually a little cylinder that I'll draw in cross-section here. And this cylinder is usually held at a very high voltage difference as well, which causes some electrostatic lensing. So the electrons that come through here actually focus down to a beam. And of course, there are some steering magnets here, both in vertical and horizontal dimension, and that causes the beam to sweep around. This little plate you can modulate with a data signal to control the intensity of the beam, and voila! You have black and white television. State of the art for 1940s, right? And so I would teach this. And of course, back then they were still using CRTs in 2003. And the students were so happy. They would go home and they said, oh, wow, I was at the Thanksgiving dinner table and I explained to my parents how the television worked. And they thought they were getting such a good deal sending their children to Georgia Tech. And then, 2 years later, I gave the same lecture. Everybody was asleep. Why? Because they were all using flat screens. It was like the fastest uptake for technology. So there's a lesson for you. 2 lessons, really. 1 lesson, don't get too wedded to your ideas or your technology because it's going to change in a heartbeat. It only takes a few years for something to be completely obsolete, no matter how cool it is. The upside, though, is that first principles are first principles no matter what they are. If we just take this device and we cut off the screen and we reverse the polarity, we have an ion drive. Now, what is an ion drive? You take a source of ions, a propellant of sorts. You heat it up and you rip off some of its electrons. So now you have a heavy positive ion and some electrons that are kind of floating around. And if you've reversed the polarity, you're going to accelerate the ions in a particular direction out this way. And then you're going to complete the circuit by letting the electrons jump back into the ions as they're accelerated out in the electrostatic field here. And of course, you do that because if you didn't have that circuit closure, you'd have this negative charge building up on your spacecraft, and eventually they would electrostatically attract all of those positive ions that you were throwing out the back, and you would slowly lose thrust and effectiveness in your ion drive. Now, what's the nice thing about this? Why do we use this? Why is this an alternative? Here's the problem. Ion drives are terrible at providing thrust. An arrangement like this typically only provides 1/50th of a pound of thrust. Well, what good is 1/50th of a pound? Well, in space, where you don't have to overcome air resistance, it's actually pretty decent, provided you can turn it on for a long time. You turn it on, you let it go for a long time. That 1/50th of a pound, if exerted continuously for days or even weeks, will integrate to a very large acceleration. And what's more, you achieve that acceleration with relatively little fuel. Because in this case, the fuel the thing that you make the positive ions with, is really being only used as the momentum, as the propellant. It's not actually being used as a source of energy. In the rocket, the fuel has to do both. And therefore, that limits your options. You have to have these energetic reactions and something that's going to make hot gases come out of your nozzle. In this case, the actual power can come from things like solar cells, because the energy for generating that momentum is electrical in nature. That's where you're going from an electricity to a mechanical form of energy, kinetic energy coming out the back. So if you come up with, the real trick for the ion drive is to come up with a really dense liquid fuel that ionizes easily. And if you can do that, then you're in pretty good shape. Let's go ahead and pick some fuels out, some candidate fuels, using the periodic table. So for this, I'm going to switch to the document camera. I think I've actually oriented it in the proper direction. This is a fun class. We get to do chemistry. Did you ever think you'd see this stuff again? Here's the periodic table of elements. And we are particularly interested in this column over here, the noble gases. Why are they called the noble gases? Because they're snobby nobility. They don't bond with anything under normal circumstances. They are the only monoatomic substances that occur naturally as gases. All this other stuff like fluorine, oxygen, nitrogen, hydrogen, these are all diatomic when they're in their natural gas state. So these are gases. However, the nice thing about the gases is that under relatively reasonable temperatures and pressures, we can liquefy them and put them in a tank. So if we had to carry a giant balloon into space, these wouldn't fly. But of course, these can be stored compactly under reasonable conditions. And really, it comes down to picking one that has a high enough mass to use as a propellant. The higher the mass, then the more momentum we can impart to it and use as a propellant. So, of course, helium is off the table because it's just too light. Too light. It's 2 protons and 2 neutrons. No good. Neon, very abundant in the Earth's atmosphere. We obviously use it for lighting and that sort of thing. But, again, too light. Argon, very abundant, again, in the Earth's atmosphere, and it's getting a little bit heavier. That's a candidate. Again, krypton, very heavy, atomic weight of 83. That has been used in ion drives because it is particularly heavy. And then there's the real nice one, xenon, a little more rarer than these other elements, but in mass, it makes a very good propellant because it's so dense. 131 is its atomic weight. Radon, of course, is the densest of them all, but there's, of course, some philosophical and biological reasons why that's difficult to procure and use as rocket fuel. So we don't usually use that one as a propellant. It's a highly radioactive. It decomposes into lead and some other particle naturally. Although there seems to be an abundant source in my basement for some reason. No, just kidding. So these are candidates. Xenon is particularly well suited. So xenon and krypton, I think, do the lion's share of propellants for ion drives. And so what's the usage model for this drive? You can't get into space with it, but you turn it on. And these are particularly useful devices for taking a spacecraft from low Earth orbit into a higher Earth orbit, like up to geostationary Earth orbit. Or let me go ahead and turn off the document camera here. And other higher orbits. And it's not nearly as fast as the Holman transfer, where you burn conventional rocket fuel smartly at 2 different locations in an elliptical orbit to quickly transfer the spacecraft. However, when you look at the entire package, the size and weight of the drive, the size and weight of the propellant, even though it may take many days to get that spacecraft into geostationary Earth orbit, the ion drive tends to be cheaper in and of itself to launch into space than the stage of a conventional rocket that would take it all the way to its higher Earth orbit. So those are candidates for going to higher Earth orbit and also for deep space missions as well, because you can turn them on for a long period of time. You're going to be spending years to go into outer space and to visit, say, the outer gas giants of our solar system. And I actually think the very first space mission in the 90s that used an ion drive was a NASA mission to the asteroid belt where you were going. It was going to take several years to get there anyway. Why not turn this thing on and get there a little quicker using minimal mass? So, and we actually have some research at Georgia Tech, several faculty members that are doing some interesting research in ion drives. We see that used more and more. Now, we're kind of blurring the lines here. There are launch systems for which we always use rocket fuel. And we use some of those same types of techniques, as well as ion drives and a larger class of rocket fuel systems for orbital control systems. That is, controlling the orbit once you get into space, placing it into a final orbit, and then maintaining that orbit, doing the minor corrections that are required. And then there's also attitude control systems, which also has to do with positions, but it's a different ball of wax. So you can imagine I've launched a satellite. It's in stable orbit. I can fire my little thrusters to weakly adjust it and keep it in the orbit that I'm desired. But there's a whole dimension of orientation that we haven't addressed. And this is important, especially if that satellite has a communications dish or directional antenna that must point to a certain spot on the Earth to maintain a radio link. Or it's doing some sort of measurement with a camera of the surface of the Earth, or some sort of observation. How do you maintain the orientation of a satellite for this type of thing? Okay. So I'm going to draw a couple different types of spacecraft. Spacecraft come in a lot of different shapes and sizes, but generally speaking, there are a couple basic body types, and a lot of it has to do with how the attitude control for the spacecraft works. How do you stabilize the spacecraft in space? And so one of the simplest ways to do that is to make a drum-shaped satellite. You plaster it with solar panels, and when you launch this from your rocket, when you deploy this payload, you give it a twist. You spin it. In fact, these are colloquially known as spinners in the satellite industry. Or, if you want to be official, single-axis stabilized. Because basically, when you spin this, this imparts angular momentum along an axis, and this satellite will hang there, and by conservation of angular momentum, will stay oriented along there, not unlike a gyroscope, as it revolves around the Earth. And so you don't really need a lot of fancy attitude control systems once you've done that. It is good to have maybe some little thrusters on the side so that you can energize, spin up, or de-spin, depending on how your spacecraft is performing. And one of the issues here, there are a couple issues. You've greatly simplified the attitude control when you build a drum-shaped satellite like this and spin it in orbit. However, there are a few things that you have to be aware of. First of all, you need power. And so the power source of choice in space, especially for Earth-based satellites, is almost always solar cells for their longevity, amount of power that they put out. We'll get into power spacecraft subsystems in a few minutes. But you usually plaster this thing with solar cells so that as this thing spins around, one side of it is always facing towards the sun. Now, it's not the best use of solar cells because if you do a quick calculation, only one side of the drum is facing the sun, and a lot of the facets of that side are not optimally oriented. They're kind of off to the side, so they're not collecting maximal incidence. In fact, what you find is that if you were to compare the output of a drum-shaped arrangement of solar cells to an arrangement of solar cells that were flared out into a flat sheet, the same area, you would only be getting about a third of the power from the optimally pointed flat solar panel. So one of the downsides is that these solar cells are only about one-third efficient. But they don't require any fancy pointing or actuation in order to operate. They're always going to be pointing towards the sun. And then the next challenge that you have is that, okay, you've stabilized the orientation of your spacecraft, but you now have a platform that's moving. So how do you do communications? Well, a typical way is to take either the direct communications antenna or a reflector, often, and you de-spin it, meaning that this is now connected to a rotary mount, and you de-spin it at the same rate that you've spun the satellite, so that the reflector is always facing towards Earth. Now, how do you always make sure that it's facing towards Earth? You have to equip your satellite with some sensing systems. Quite often, an infrared type sensor is used to actuate the antennas and figure out which side the Earth is on. The Earth is relatively hot compared to the blackness of space, and so it's relatively easy to build a sensor to actuate the position of the Earth. And so this thing is spinning around. The reflector is de-spun, and often there's a small directional antenna like a horn or a variety of types that we'll learn about later that radiates up to this reflector and either sends or receives a signal from the surface of the Earth. So that's a spinner. That's one shape. You've probably seen that before in schematics or pictures of satellites. Another one that is very common is a three-axis stabilized and this is your classical box with solar cells, solar panels sticking out of it. These are movable joints so that the solar cells can be oriented towards the sun. And so your control systems go inside the box, as well as a unit that has momentum wheels. That either spin up or spin down depending on how you want to orient the spacecraft. keep in mind that if I were to put this spacecraft pointing towards the Earth, and if I wanted to, let's say it was in an equatorial low Earth orbit, and I gave it just enough spin so that its rotation was 1 sidereal day. And so therefore it would be sort of phase-locked with the Earth as well. It would rotate almost as fast as it would, well, exactly as fast in theory as it would go around the Earth. However, over the course of many orbits, errors would build up, and eventually the thing would be pointing off into space. So we always need some sort of way to do attitude control and to have a dynamic system, one that can sense and then adjust the attitude of the spacecraft depending on the current state. Do we need to tilt a little to the left or to the right? And so for that reason, we have these momentum wheels on board. You need at least 3 to do 3-axis stabilization. Most spacecraft have at least 4, because if one of the mechanical components would fail, the control system can adapt and just use the remaining 3 momentum wheels to spin up or spin down and do orientation control. And so these 2 types kind of account for the different bodies that you see on spacecraft. There are some spacecrafts, especially in the world of very small picosatellites, where they don't even bother with attitude control. You just let the thing tumble around up there. For example, there's a whole class of satellites called CubeSats. This was pioneered about 15 years ago as a way to do very inexpensive launches with a standardized shape of a satellite. So a CubeSat, if you ever hear anybody use that term, if you have a 1-cube CubeSat, you basically have a satellite that will fit in this 10 by 10 by 10 centimeter cube. And this is a convenient form factor that can stow away on the payload, as a payload on a much larger satellite launch. And thereby, it reduces the cost of the launch of a satellite. It turns out that the electronics nowadays are getting so compact and power efficient and varied that you can actually do a lot in a square, what is this, a liter? In a liter of electronic space, you can do quite a bit of sensing, communications. And you can squirrel it away, and the launches are typically about $100,000, which is pennies on the dollar compared to the launch costs of most satellites. And fitting in this standard form factor is particularly nice because, you have these CubeSat launchers that are on payloads now where you can dump a bunch of these into this standard geometry and launch them. There are some satellites that you can it's almost like Legos, right? You can actually make a satellite that's 1 cube by 3 cubes, 1 by 1 by 3, or use some variant of the CubeSat architecture, some integer multiple, to make a slightly larger satellite if you need the available space. But this is a whole class of satellites that's gained quite a bit of popularity. Students can build these, and if you rattle the tin cup enough, you can get it launched on a larger space mission. In fact, I'm pretty sure that this year I'm going to do a CubeSat-based project in this class. So one of the applications that's been very intriguing of late, the companies like Google and some startups in the Bay Area are interested in launching a platform of CubeSat satellites, 10 centimeter by 10 centimeter by 10 centimeter, putting a constellation up around the Earth of these, and then photographing the surface every day, which is a tremendous undertaking, both from a sensing perspective and also a communications perspective. You've got to get all that data back down to Earth. And so since the satellite project is always ripped from the headlines of today's technology periodicals that dozens of people read across the planet, we are going to do something related to that, I believe. And so this is a common third architecture. The CubeSat usually just tumbles in space, so you use something that's not particularly directional to do communications, something that's relatively omnidirectional, which we're going to learn really hampers your link budget. But if you're in low Earth orbit and you've got enough signal processing and you're not taking up too much bandwidth, you can do communications with that. Just blast it out everywhere and hope planet Earth is in one direction. That's the philosophy of the CubeSat. These types of satellites are often called picosatellites. And represent a sort of third form factor that you'll see spacecraft take nowadays. Any questions so far? Yeah.
Cells on the solar cells.
Yeah, you usually put at least a few solar cells on every facet of this thing to make sure that you get some sort of pickup, since you don't have any real attitude control. I think some people have tried to put little momentum wheels on here, but usually the space mission is not super sophisticated. You're usually trying to measure one thing with the CubeSat or do one basic task of communications. And so the power demands aren't that high, and you can get away with just a couple of solar cells plastered over the device. You could, as long as you fit within 10 centimeters, you could come up with a more sophisticated CubeSat that would unfurl a solar panel in space, or unfurl a nice dish antenna to go back to Earth. There are actually some people that are looking at inflatable dishes or unfurlable dishes like that for CubeSats in space to beef up the communications. But as we're going to learn in about a month, if you can exchange a non-zero amount of power between 2 points in space, you can also exchange a non-zero amount of information. So you won't be streaming video on your CubeSat, but you will be able to do some basic telemetry data, even if the antenna is just a crummy omnidirectional thing that can't point. So we'll do some analysis to show that. That'd be a fun workout problem in class. Okay, any other questions? Good question. Yeah?
Once it's deployed, is the antenna still internal to the box?
Yeah, so the CubeSat, often the CubeSat is not a solid box. I should bring some pictures in. In fact, I don't know, do our friends in the aerospace department, do you know anybody working on CubeSats right now? Oh, he got the finger pointed at you. He threw you under the bus again, by the way. So, yeah, is there like a frame you could bring in at some point or some pictures? We should do show and tell at some point. That would be fun. But a lot of times the CubeSat, it has to fit in a 10-centimeter cube, but it doesn't necessarily have to be solid. So a lot of times it's just a frame, and then the inner electronics are in here, which means you can put an antenna in the gap there so it's not influenced by the metal nearby, which, as we'll learn, is a terrible thing for antennas to have to radiate in the presence of other metal. Some people even have talked about using the superstructure itself as the antenna, designing it in such a way that it will actually radiate. That depends on the frequency and some other issues that we'll get into. Good question. Any other questions? What is your CubeSat mission doing? Are you at liberty to tell?
Yeah, it's using a camera to look at other space objects.
Oh, okay. Cool. Trying to track down other orbital debris kind of thing. Oh, neat. CubeSats that find orbital debris. Even though ultimately they're probably contributing more to that problem than... No, they're not. This is good. Okay. Well, if there aren't any other questions about attitude control and launch systems, let's talk briefly about some of the options that are available to an engineer in terms of power systems. We're electrical engineers, and we often take it for granted, but we can't in space. In fact, this is one of the most daunting aspects of doing business in space, is that you can't plug in the satellite. The satellite literally has to live forever in space during its entire usable lifetime, and it must take all of its power, or at least its power conversion hardware, with it. And so there are generally 4 classes of power systems that you choose for your spacecraft. The first one, batteries, in a way, all the spacecraft have to have some sort of battery backup on board, something rechargeable that you can recharge, top off, and then use if something should happen to your spacecraft unexpected, or at least something that happens infrequent enough for you to actually plan around. For example, let's say you've got your 3-axis stabilized satellite, and for one reason or another, it gets misaligned and the solar cells no longer point towards the sun. Well, now you've just lost power. Or if it passes by the shadow of the Earth. Maybe it's in geostationary Earth orbit. You think, well, that's far enough away. Because everything's not aligned, as we learned earlier, you don't really have to worry about passing through the shadow of the Earth, except for maybe once in a blue moon. And if you lose power, it's just a chicken and an egg problem, right? How are you going to have enough power to wake back up and orient your solar cells properly so that you get the power to do continued operation? And so batteries are, in some form or another, are a necessity in spacecraft operation. They have a short lifetime, limited power output. You can't drive really heavy loads. They need to be rechargeable, usually. And one thing that you don't think about in space is that battery chemistry is heavily temperature dependent. And so the battery is usually encased with some sort of thermal and radiation protection so that it's not exposed directly to the sun. However, if you're in the shadow of space, the temperature plummets, and you're well below freezing. And, of course, if you ever learn anything about batteries, is anyone from, like, Minnesota or one of those really northern states? You have to plug in your car before you actually turn it on. It actually heats up the engine block and the battery before you turn it on. Does anybody know what I'm talking about?
Yeah.
You're from in Alaska? Yeah. See, they had the plug-in vehicle long before the rest of us did. They just weren't using it the way that we do, right? And so because of that, and again, now you have this chicken and the egg problem. Oh, you said, well, I just got to add a thermal warmer to my battery to make sure it operates in space. Well, wait a second. How do you drive it? Do you drive it from the battery? No, you drive it from the solar cells. Well, what if you get in a shadow and you lose power for a few minutes? Does your battery then cools off and you can't run the heater? And so what they typically do is they make these hockey puck type warmers that you put in with your battery. They contain some heavily encapsulated radioactive material to heat the batteries. This is material that has a half-life of, I don't know, 10 years or so, and it will slowly stay warm at a reasonable temperature well over the lifetime of the battery that you're designing. And so at some point when the radioactive material runs out and it can no longer maintain the acceptable temperature, you design it to a certain length so that all the other subsystems are also failing at the same time in the satellite. You're running out of station keeping fuel. Your solar cells are dying. And all the other spacecraft elements that are time limited are falling apart as well. So that's a lesson to you. Never buy a used satellite, right? It's worse than a car. Okay. So that's simple, batteries. Now, of course, what we really want to use are solar cells. Because the sun shines 11 times more intensely, or at least there's 11 times more harvestable power in space than there is on a bright sunny afternoon on the surface of the Earth. And the sun never sets in space. So aside from a little bit of shadowing around a planet or a moon or something like that, you don't have to worry about the sunset. So it's this limitless, ridiculous amount of energy that's available to you. And this is hand-in-glove fit, at least it would appear, in terms of how to get your power in space. And of course, most satellites always use these solar cells to operate in space. The caveat there is that for Earth-based satellites, it's fine. You do have to watch out when you start looking at deep space missions. Once you get past, say, Jupiter, there's not enough solar density to drive all the power demands for a communications satellite. And so these are not useful in deep space. In fact, it used to be you could never use solar cells past Mars, but we've gotten so good at making high-efficient, broad-spectrum solar cells that you can now use them in Jupiter. I think the upcoming Galileo mission is actually using solar cells in Jupiter, which 20 years ago you would have laughed at that idea. The efficiencies just weren't there, but now we can do it. I don't know if we've actually sent a solar cell-based mission to Saturn yet, but we'll see. Relatively high energy output. And of course, that's a design trade-off in your spacecraft. I can actually make as much energy as I want as long as I'm willing to carry the mass into space. And so there's a lot of research that goes into making these high-efficiency solar cells that aren't just high efficiency, but are kind of thin film, lightweight, very space-friendly, space-hardened. Of course, it requires pointing. And the other thing to keep in mind is that they don't last forever, particularly in space. All electronics in space have to be radiation hardened. There's a lot of radiation that you experience in space that you do not experience on the surface of the Earth. In fact, the defense that I just ran over from earlier this morning was a great proposal, PhD proposal actually, about how to use special silicon germanium devices for your electronics in space, particularly your RF front-end amplifiers and that sort of thing for the communications link, so that they resist radiation effects in space. It's a very important topic because you get all sorts of effects. First of all, you have to realize when you're in space, you are right in the face of this unshielded nuclear fusion reactor we call the sun, which is just blasting radiation. A lot of that we don't experience on Earth because we have a very strong magnetic field which deflects charged particles. So all the charged stuff gets pushed to the side. When you're in low Earth orbit, there's a lot less of it that gets pushed to the side, so you experience a full front. As you go up in orbit to higher Earth orbits, like geostationary and beyond, it gets worse, and it gets worse, and it gets worse. Then there's this sort of exogenous galactic radiation that comes in from who knows where, the galactic center, weird black holes that are somewhere out there. And those are very high energy particles that can wreak havoc with your electronic design. So they cause single event failures. For example, they can cause transistors to latch up and just stop working. They can cause like blips in your communication signal, big spikes that destroy a bit or two of data. They can actually do permanent damage to your electronics. They can actually, some of them are so high energetic and they can get through the shielding so much that they can literally dislodge a dopant at the junction of a PNP or NPN transistor. And dislodge it and permanently damage the device. And so adding shielding to electronics, formulating electronics that by their very nature, because of size or dopings or current handling capacities, resist some of these effects. This is a big research study. As Professor Kressler, for example, here at Georgia Tech, does quite a bit of work in that field. And solar cells are another example of something that needs to be radiation hardened before it gets put into space. Why? Well, these high energetic forms of radiation, high kinetic energy ions, very energetic photons well beyond the visible spectrum that can sometimes strike an object in space. These can permanently damage the semiconductor electronics, especially when you've got them pointed directly towards the sun. So over time, the electronics will degrade, and the PN junctions that are putting out photovoltaic energy will slowly, over the course of years, lose their voltage and their ability to supply power. So the electronics get damaged. That's one thing that limits the lifetime of a solar cell. The other thing that you have to worry about, too, is just the optical damage. There's a lot of dust. There's solar wind. There are micrometeorites in space. And if you're familiar with constructing a solar cell, you've got to have sort of an encapsulant that's transparent, that allows light to come in and strike the PN junction, and then another encapsulant layer that completes the circuit but is optically transparent, something like indium tin oxide that you can put on the surface of that, and then the encapsulant. So you have to have these nice transparent substrates that go on top of where the PN junction actually does most of its work. This transparent substrate is perpetually being sandblasted in space by tiny little particles. And so, over the course of 10 years, that transparent substrate turns into a translucent substrate and significantly degrades the output power of the solar array. So that, between station keeping and the usable lifetime of your solar array, those are the two big lifetime bottlenecks of a satellite. The nice thing about the solar cell is you can always design it. If you are expecting half of your power to degrade over 10 years, then you make the solar array twice the size as what you need, so that when you get to that point, then you can scrap the satellite. But of course, that adds a lot of weight, a lot of mass, a lot of cost to your launch. So that's always a factor to take into consideration for solar cells. We mentioned a third type, the fuel cells, which are usually a hydrogen and oxygen combination over a special membrane that can be conducted, where that reaction can be conducted galvanically to produce a voltage. And the nice thing about fuel cells is that they tend to produce a lot of output power. You can drive a lot of load in terms of amps and volts with that. That's why people have always kind of talked about using them potentially in cars and vehicles, because you can supply the type of voltage and current that you need to drive a pretty beefy electric motor. The nice thing about fuel cells, too, is that especially if you're on a manned mission, you may have the oxygen and hydrogen readily available for that type of exercise anyway. You need the oxygen to have your astronauts breathe, for example, if it's a manned mission. So you might as well bring some hydrogen along for the ride, too. You can use it as station-keeping fuel. You can use it as a source of electricity for a short period of time. But in the end of the day, when you have spent your hydrogen and oxygen, you're out of electricity, and you have to resort to something renewable. Very mass-limited fuel supply. But for manned missions, it often makes a lot of sense. In fact, that was the problem if you ever saw the movie Apollo 13. I think it was actually the hydrogen or the oxygen tank as part of both the air supply and the fuel cell that blew up and caused problems with that spacecraft. It was the fact that it was a versatile fuel, that they had other supplies of oxygen and hydrogen on the spacecraft, either in the atmosphere or ever, that allowed them to kind of escape that tragedy, or would have been tragedy. Okay. Now, the last one. If you are in deep space, You can't use solar cells. There's no way you can do anything with just batteries or fuel cells for a long period of time. This would be like Voyager or some of those outer space missions. Your only resort at that point is a radioisotope thermal generator, known in the business as an RTG. This is very much like the little hockey pucks on steroids, the hockey pucks that you use to warm batteries. Nobody minds if you put these encapsulated hockey pucks that stay warm on a battery in a spacecraft. However, what you do is you make a much bigger pile of radioactive material. You wire it with a bunch of thermocouples, and you convert the thermal energy into electricity. And by choosing the amount and the type of the radioactive material, you can actually make a space mission that lasts for a very long time. The RTGs in Voyager, which was launched 40-some years ago, are still operating, and they're still actually powering communication systems to send signals back to Earth. It's 40 years later. So this is intrinsically a nuclear radioactive decay source. Reliable, extremely long-lasting by space standards. Now, what might you think one of the drawbacks of using an RTG is? Yeah.
Well, if you have an accident on launch, then you get a lot of radioactive.
That's right. These are politically dangerous because sometimes they are environmentally dangerous. If something should happen to the spacecraft, and remember that's very common. You read about rockets blowing up all the time on the news. There's a high-profile disaster, usually on unmanned spacecraft, but still, every so often it happens. Why? Because rockets are bombs with holes in them. And you're taking a bunch of radioactive material and you're putting it on the top of a bomb with a hole in it. And so people don't like the idea of that, especially when you're not launching anywhere in the vicinity of where you live. And so generally this technology, even though it's wonderfully bulletproof, even though a lot of engineering goes into encapsulating the RTGs and making sure that they don't disperse radioactive material, even if there is a launch failure, they're only used for deep space missions or some mission spacecraft that would require an unusual power demand that was long-lasting or higher power than what you could get with solar cells. So, those are your options. Do you have any questions so far? Yeah?
What kind of material are they using to shield the electronics? Because usually lead is used here, but it's just pretty heavy to take out there. So what are they using?
Yeah, so that's a good question. The question was, what is used to shield electronics? So all spacecraft electronics have a thin sheet of aluminum shielding around them. That gets rid of a lot of the really heavy lumbering radiation like alpha particles and things like that. And then they don't typically take lead because A, it's too heavy, and B, there's only so much shielding that you can put around a piece of electronics. You can make it thick, really thick, and at the end of the day, you will only exclude a certain type of radiation. The really high-energy cosmic rays, they're getting through no matter what you put around it. And so, the trade-off is to just put some aluminum casing around your electronics. That'll get rid of the really bad stuff. The other stuff you're going to have to live with anyway. And that's the current philosophy. And then there are a lot of other aspects to space certification of electronics. Even after you shield it, because there are some things you just can't shield against, a lot of people will make their devices in triplicate so that if, in case one of them fails during a digital operation, you sort of vote and you take the best of the three that are coming out, the best two of three, so to speak. So that's an example of actually how you alter the design of the hardware itself to withstand that sort of environment. And then there are some exotic materials that you can make transistors and electronics out of. You can use vacuum tubes in some cases if you're desperate. That in and of itself, space certification of electronics would probably make a nice course in and of itself. It would be kind of neat. There are a lot of interesting places that you can actually test the electronics, a lot of laboratories that try to reproduce on Earth the radiation conditions that you would experience in space to see how your electronics would actually perform. And it's typical to send your spacecraft before it goes up on the launch vehicle to one of these laboratories to certify its operation under those conditions. That's an important step in launching your spacecraft. Any other questions? Good questions. Okay, now we get into the meat of the course. We do one last subsystem, which will introduce us to the communications and the electronics that we'll be spending most of the course talking about. That is the RF subsystems, radio frequency subsystems. And this is a good chance for me to introduce, at least at a block diagram level, some of the terminologies that we're going to be using in satellite communications to discuss systems for the rest of the class. So what I'm going to do is sketch out a typical arrangement for a bent pipe transponder. What is a transponder? A transponder is a device that receives and then retransmits an identical signal, whatever it received. What I'll put up here is an example of an analog transponder. One of the mainstays of satellite communications 20 or 30 years ago. Most systems have migrated towards digital, but we'll still need to understand the basic analog aspects of a satellite subsystem to understand the limits and engineering choices that face an engineer who's doing a digital system. And it'll introduce you to all the block diagram terminologies that I'll be using in class. And the concept of spectral analysis, too, which you can never review that stuff too much, right? And so a bent pipe transponder in satellite communications does exactly what the name suggests. I think they named it after the Bugs Bunny cartoons. Do you remember seeing those, Bugs Bunny? Like the hunter would be after him with his shotgun, and he'd shoot the gun, and the shot would come out. And Bugs Bunny would take a pipe and like make a bend, a U-bend, and the shot would go in and then come out that side, right back to the hunter. That's exactly what this thing does. It takes a signal from Earth. It sends it right back down to Earth. However, you got to change frequencies, and you got to clean up the signal a little bit, at least amplify it so that you have enough signal-to-noise ratio back on Earth to receive what was transmitted. So, what are the components of a bent pipe transponder? Here, this is the universal symbol for antenna, the bent coat hanger. Doesn't matter what antenna type. This might be a dish. This might be a helical antenna. It might be something exotic, a horn, a dipole. It doesn't matter. When you're block diagramming, this is your receive antenna. The signal comes in here and goes to a block. The first thing you do when you receive the signal is you make a bandpass filter, BPF, bandpass filter. And, of course, I draw filters. We'll have low-pass filters, high-pass filters, notch filters. It's a pretty standard terminology in block diagramming communication systems. This is a low-pass filter. It blocks the high and the medium frequencies. I drew a bandpass filter that has the high and the low blocked out. It lets this one through. If you want a notch filter, you notch out the center frequency you want, and you let the stuff above and below. Very simple convention, very convenient for diagramming. This is the device that many of my Georgia Tech senior design students like to make. You won't be seeing that in this course again. Okay, you filter. Why do you put a bandpass filter there? Well, this antennas tend to be resonant objects, which means they only receive over a narrow band. But they still always, there's no such thing as perfect exclusion. They're always going to receive some signal strength out of band. Even if they're not designed for that frequency, they're going to get something. It may be 30, 40, 50, 60 dB down. But they're still going to get something. And if you get enough of those signals, you can cause interference or saturation in your amplifiers down the RF chain, which is bad because then nobody's going to receive anything. And so generally you put a little bit of filtering so that all of your out-of-band signals are attenuated somewhat and your in-band signals drop right on through. I say a little bit of filtering because you don't want to put too much there. When we do noise analysis of RF change, we'll see why. This is where the signal is the most fragile. The signal-to-noise ratio is the lowest, or the highest it can possibly get, I should say, at that point. Anything you do to it, you have to be careful what you do to it, because anything you do to it is going to degrade that signal-to-noise ratio. Adding a bandpass filter will not, if it's a passive bandpass filter, it will not add any signal energy. It can only really add loss, which will degrade the signal-to-noise ratio. To make a really tight filter in electrical engineering, something that has extremely tight stop frequencies, implies that you may need to add loss in order for that to happen, which you don't want to do at this point in your chain. You just want a little bit of filter, because all you're really doing at this point is trying to bang down any really strong close band, out-of-band interferers that might be leaking through your radio chain. Worry about the really tight filtering later in the process. You'll see where that occurs. There's just a little tidbit for RF engineers out there. Then this next device is where you want to spend a lot of money in engineering. This is your low noise amplifier. Let me write out these acronyms since it's the first time we're encountering them in class. Low noise amplifier. And this is, of course, band pass filter. All amplifiers in this class are triangles, but this is a special kind of triangle, a low noise triangle. Why? It's made out of a device whose materials and whose biasing and electronic configuration is meant to add as little noise into the signal as possible, because this is where my signal is the fragilest. So I have to have an amplifier that's designed not to give a lot of gain, but really just to give a little bit of gain without adding a lot of noise. Because, you know, whatever noise comes in at this point, you're amplifying from here on out. So I got signal, I got noise, I'm amplifying them both when I run them through that. Well, I would much rather amplify a little bit and add very little extra noise at that point. And then in subsequent stages, I can buy cheaper and higher gain amplifiers that subsequently raise everything up a lot more. Those can add a lot more noise into the system relative to the first amplifier, because you've already got a strong signal at that point. So this is your critical component electronically, the low noise amplifier. There's always going to be an LNA present, the first active device that you usually see in a receiver chain, whether it's a cell phone or a satellite system. And then, in a bent pipe transponder, you do a mixer, which is usually drawn as a circle with a time sign in front of it, because it effectively does multiplication. You take an oscillator, we call this a local oscillator. This generates a sine wave of a certain frequency in your satellite system. And you mix it with this thing. Now, what does that do spectrally? Okay. Now, here I do a little bit of spectral sketching so that we understand and are all on the same page about what's happening. If I look at the frequency domain of a signal, I got a voltage signal as a function of time coming in to that from that antenna. It is an RF modulated signal usually. It means there's going to be a frequency, which we'll be calling the carrier frequency, F sub c. And because I'm an academic, we teach Fourier transforms. To be mathematically correct, there's always a positive spectrum and a negative spectrum, right? And so I'm going to draw a little negative F of c. And so if I took the Fourier transform of that signal, and of course squared it, because I can only really draw the magnitude of a Fourier transform squared on a two-dimensional board, what would I see? I would see a data signal that was band limited with an RF bandwidth, we'll call it capital B. This is my RF bandwidth. And I would see the mirror image over here. How do I know this is the exact mirror image of that in the spectrum domain? Magnitude squared of the Fourier transform. How do I know that the magnitude of the Fourier transform has the exact mirror image? What signals in the time domain behave like that? The signal is real. Perfect. If I have a real valued time domain signal, the Fourier transform of that signal in the frequency domain is always the conjugate mirror image of the left and the right side. In other words, x of f is always equal to the complex conjugate of x of minus f. Which means when I square it, I really get the same signal shape. That's true of real valued signals. Now, in telecommunications, quite often you'll deal with complex non-mirror image spectra that result in complex signals. And the reason that is quite often you'll do something called baseband analysis, where if I were to look at, okay, I can't draw complex on the graph here. Use your imagination. Let's say this is the complex spectrum that is on a carrier frequency, the actual signal, x of f, modulated onto a carrier. It's a conjugate mirror image the way that I've drawn it because it's a real valued signal. It's a signal I can actually observe in the time domain when a real valued oscilloscope, there's no such thing as an imaginary valued oscilloscope, and I can see that signal, and that would be its Fourier transform. For analytic convenience, however, telecommunications engineers, particularly those in wireless communications, like to move this down and call this baseband equivalent spectrum, where they take one lobe and move it down so that the center frequency is now at 0. This is called baseband equivalent signal modeling. And in that case, in order to not have any loss of generality, you have to have a complex time domain waveform. It's not going to be the complex mirror image anymore. So just be aware of that as you look at papers and textbooks from this field and the field of wireless communications in general. if you ever see complex signals in the time domain or spectra that is not the conjugate mirror image, you're usually dealing with a baseband equivalent model. And sometimes the authors make that clear, and sometimes they just kind of start doing math and assume that you know what they're talking about. And like, where did all these complex numbers come from? Oh, they just did a baseband equivalent representation of their signal and the channel that it goes through. Okay, so now, what happens, let's say, go back to our diagram here. I have a signal that's centered on, let's say, 6 gigahertz. And it's coming down the chain. And it encounters a local oscillator that's, let's say, is 2 gigahertz. What happens when you multiply two signals like that? Okay, we said the 6 gigahertz signal in the frequency domain looks like this. It's got some information centered on FC and minus FC. That FC is going to be 6 gigahertz. And then I've got a local oscillator. In the frequency domain, local oscillator is just a cosine wave, right? Centered at 2 gigahertz. And so it has a really easy signal spectrum to draw. It's just 2 impulses at plus and minus 2 gigahertz. I multiply them together in the time domain. What does that do? Okay, so here's a little mental exercise for all of you signal processing engineers out there that love the Fourier transform. We can do this in our heads without resorting to any mathematics. And in fact, when you learn the Fourier transform in electrical engineering, it got you out of doing something that was really painful. That started with C. Do you remember what it was? Convolution, that's right. When you probably took your first double E class or your second double, I don't know where it showed up in your curriculum, the teacher taught you how to do a convolution. It's that folding integral. It's basically how you calculate the output response for a given input if you have the channel impulse response or the impulse response, right? If you know what the impulse response is, you can take any arbitrary X input, convolve it in the time domain with the impulse response, and voila, out pops the output, and you've pretty much solved the system. The only thing is that convolution, when you did it by hand those first couple times, it was a pain, right? You had triangles and boxes, sine waves, and folding, and you had to keep track of your limits of integration, and it was a nightmare. And then, like the savior, your instructor swooped in and said, you will not ever have to do a convolution again. All you need to do is multiplication, because if you take the Fourier transform of your input and your impulse response and multiply them together, you get the output. So the Fourier transform turns convolution in the time domain into multiplication in the frequency domain. And you don't know how many countless hours that has saved you and me during the course of our engineering career for a linear system. Very useful theorem. There's another really interesting property of the Fourier transform. It's the idea of duality. The idea that what works in the time domain also works in the frequency domain and vice versa. So, if convolution is actually multiplication in the frequency domain, convolution in the time domain is multiplication in the frequency domain. Multiplication in the time domain is really what in the frequency domain? Convolution. And so when I look up here at this diagram, I'm multiplying two signals, a sine wave and an informative signal on a carrier here. I'm multiplying them. Really, I just need to convolve them in the frequency domain. And that tells me what the signal is actually doing. And this is one of the very rare instances in life where convolution is easier than just about any other operation you could do to these two signals. Why? Because if I convolve this spectrum with this spectrum is just two impulses. When I convolve an impulse with something, what do I get? I get itself. That's the only useful convolution to do by hand, right? If I have an impulse and I convolve a function with it, I just plop a copy of that function down where that impulse lies, whether it's the time or the frequency domain. That's just a basic mathematical property. So when I multiply these two in the time domain, I convolve them in the frequency domain, and what happens, I just take this signal, I plop a copy down, centered at 2 gigahertz. That means over here, 6 gigahertz away, I have some informative signal, and 2 plus 6, 8 gigahertz away, I have my other copy. So that's the first copy that I plop down at negative 2 gigahertz. That puts this peak at 4 gigahertz and this one at 8 gigahertz. And again, I have positive 2 gigahertz. I'm going to have to plop a copy of this signal down right there. That'll put a lobe there. One at positive 8 and one at negative 4 gigahertz. So now, as the output of that mixer, I've got 2 copies of the incoming spectrum, and I need to get rid of one of them. In this particular example, I'm going to get rid of the high frequency component, the 8 gigahertz, so that only coming out of here is 4 gigahertz. The signal spectrum is going to look like modulated information at plus or minus 4 gigahertz from here onward. I then run it through some more amplification and perhaps another stage of amplification. This one would be a high power amplifier. This would just be a regular amplifier, but my last stage is meant not necessarily to give 30 dB of gain, but rather maybe to give 10 dB of gain and supply a lot of the power I need for communications, to supply a few hundred watts, tens or hundreds of watts for satellite communications in most circumstances. And then that feeds into your transmit antenna, whatever it may be, that sends the signal back to Earth. And there you have your classic analog bent pipe transponder with the architecture of the first commercial communication satellites back in the 60s and the 70s and the 80s. Maybe there's still a few analog satellites up there. Now, what's the problem with this architecture? What do you notice about this? What might be some of the drawbacks? What are some of the benefits? Benefits or drawbacks? Shout it out. Not all at once. Yeah, simple. That's really good for a spaceborne piece of electronics, right? You don't want something that's going to have a lot of parts that are going to fail. Which communications protocol does this work for? Which standard is this? All of them. That's right. All of them. This is protocol agnostic. You can come out with version 12.9 of your modulation scheme, and this will still operate. So that's a really good thing. How about some drawbacks? We haven't talked about those yet. Well, this is, if in classic telecommunications terms, this is considered a non-regenerative repeater. It just takes the raw signal, amplifies it, and spits it back out. The signal to noise ratio, even at the output, will never be any better than at the weakest point in the RF chain. Just because you've amplified the signal strength up to a certain degree, that noise is along for the ride and also got amplified, at least the noise that was in band. So that represents a plateau of performance that you'll never be able to overcome. Down at the Earth, you're going to add in more noise and interference to that signal that's already been corrupted. And so your signal-to-noise ratio on Earth is even worse than up here. If, however, and this is how most modern satellite transponders work, you use what we call regenerative repeating. You actually demodulate the waveform, decode it, get the best estimate possible of the digital bits, then re-encode everything and remodulate it and send it back down to Earth. That's a much more effective strategy. Why? Because digital communications is kind of magic. It really is. It's not like the old days of analog television where, you would be losing power and the picture just got a little crummier and a little crummier, but still watchable, and then crummier and crummier. And there was this really wide range where you get really low signal noise ratio. You could still pick out something going on in your favorite television show. And if you had a kid, you actually had the patience to watch it, right? I remember, as a kid myself, watching, I used to do the analog scrambling of cable television. And, you would see a really cool movie on your grandparents' HBO box, but they didn't subscribe to HBO, so there was this you put it on the adjacent channel, and then you kind of tweaked it, and then you saw this wavy version of, I don't know what it was, Star Wars or something that was popular in the 70s or 80s. And it was terrible signal fidelity, but you could still watch it because it was analog. Digital is completely the opposite. A well-engineered digital system will work perfectly down to a certain signal-to-noise ratio, and then it stops working altogether. But signal-to-noise ratio is mercifully much lower than the analog signal for what is usually tolerable communications. This is why we use digital communications. You can engineer it to almost an arbitrary level of accuracy and precision. You just need to have the right ingredients, bandwidth, signal strength, etc. And so if you can regeneratively repeat the signal, you tend to get a much cleaner low bit error rate transmission of data, particularly digital data. And so this is what a more modern satellite would do. You can actually do variations of this where you have maybe multiple stages in your transponder, even an analog transponder, where you mix a high-frequency signal down to what's called an intermediate frequency. This would be down at maybe the hundreds of megahertz or 1 gigahertz or something like that. And that's a nice frequency to operate at because it's much easier and cheaper to make good amplifiers with low noise figures, high gain, high linearity, high Q, or you can get the same bandwidth with a lower Q filter. And so that heterodyne architecture, which is used in many radios today, most radios, this is using multiple mixers to mix down and then back up to whatever your desired frequency is. Or down, clean up your signal, and then move it down to baseband so that you can demodulate it. We'll do that operation later in the class. But this is the basic gist of how a transponder would operate. How are we doing on time? We have about 9 minutes left. Any questions so far? No perfect understanding? Well, you do the same similar operations on Earth. Let's diagram a typical Earth station receiver. Here's your dish antenna. The dish takes your beam in, focuses it to a small antenna element at the focus, And now we've got to turn that signal into a baseband signal. So if I block diagram that, here's my RX antenna. We put a little bit of filtering, just like we did in the spacecraft. This is a universal RF principle, no matter where you are. Here's your LNA. And you have a local oscillator. Let me actually draw it. A circle with a squiggle in it. That's your local oscillator. Bandpass filter. Regular amplifier. And here's an example. This device takes your high-frequency RF, which could be very high. In satellite engineering, we've been using millimeter waves for decades, way before it was cool for the terrestrial researchers to talk about. Why? Because, first of all, millimeter waves, nobody's using that spectrum, so it's up for grabs in terms of satellite engineers. You can build highly directional antennas, as we'll learn, when the wavelength gets really small at millimeter waves. In fact, we would love to use really, really high frequencies. The only thing that limits us in satellite engineering is really atmospheric absorption. And that pretty much puts a damper up on around 60 gigahertz as to what's the highest frequency. There are a couple windows that open up after that, but for the most part, we don't really get much beyond 60 gigahertz out of the atmosphere. That sort of puts an upper limit on the frequencies that we can use in satellite communications. Up and down. But of course, 60 gigahertz, that's nothing to sneeze at even in the year 2015. Signal transport, once you get out of the atmosphere, actually gets really hard at 60 gigahertz. You can't use coaxial cable. It's too lossy. You can only go millimeters in a coax before you lose signal. You can use waveguide, but even waveguide at 60 gigahertz is really lossy. And it's not particularly convenient to put a little horn antenna at 60 or any millimeter waves and then use your erector set of waveguides to route this to your little communication shed. Waveguide is not a very low-cost or flexible medium to do your signal transport. So as a result, usually you put something like this when you're doing high-frequency reception at the front feed line. So you got to run some DC power to this because there are active components here. But this will take a high-frequency signal, move it down just the way that the transponder did, the bent pipe transponder, move it down to a reasonable frequency, maybe in the megahertz regime, where then you can screw in a coaxial cable and do your cable runs to your communication shed. This is called a low-noise block converter. Sometimes just LNB or low-noise block to those practicing satellite engineers. Have you ever hear somebody talk about a low-noise block in LNB? That's what they're talking about. Okay. I'm going to leave it at that. That's the end of our astrodynamics and spacecraft subsystems series of lectures.